We've been talking about the way in which ideas and behaviors spread through social networks. You see your friends in the network engage in some behavior, maybe buying a product or joining a social movement, holding a certain opinion. You think about what that implies for you, and you make a decision. Should you engage in the behavior also? And sometimes we say that such a behavior is spreading contagiously, right, from person to person through the network. And when we do that, we're invoking an analogy to contagious diseases, right, actual biological diseases. Now we'd like to actually switch to that issue directly and think about how epidemic disease spreads through a network. And epidemic disease is really a place where biology and networks come into close contact because we have a biological pathogen that's infecting people, but it's spreading from person to person on a contact network, right? The graph of people where there's an edge joining two people who've come in close enough contact that the disease might spread, right? So with something highly contagious like the flu, maybe you sit next to someone on an airplane who's sick, and you can end up catching it that way. With other kinds of diseases, maybe closer contact is necessary. So we're going to think about that question, right? How biological disease spreads. And what's interesting is that at a mathematical level, we're still talking about the same thing we were talking about with the spread of behaviors, something moving on a graph. So why are we treating it separately? Why does it need separate consideration? Why don't the same models apply? And the real point is about differences in mechanism. So with social contagion, you were making a decision, and we actually were able to model the decision as part of the mechanism and derive the contagion from that. Now with biological contagion, there is also a mechanism, but in a sense it's a very, very complicated microscopic mechanism, right? So this pathogen enters your body, it triggers an immune reaction, you get sick, you're contagious, you pass it to other people, and the same process repeats. And modeling that is, of course, an important thing to be doing if you're trying to fight disease. But if you want to understand the dynamics on the network, it's been very hard to turn those kind of models into something mechanistic. So instead, we're going to do something totally different. We're just going to model it as random. We're going to say this thing is so complicated, we're going to put a black box around it. And that when you bump into someone who's sick, it's almost as though a coin gets flipped somewhere. And if the coin comes up heads, you catch the disease. If the coin comes up tails, you don't. Right? Really something more complicated was happening, but the randomness has abstracted that away, right? So in the contact network, you meet someone who's sick, just there's this random chance that it jumps to you, right? A single conceptual coin flip, right? Not a real coin flip, but that's what we'll use in the model. And what we'll find is that actually once we develop such a model, it actually becomes useful in social contexts too. And so people studying the spread of behaviors in situations where the reason why the behavior is spreading is so complicated that it's very hard to model the decision, have actually gotten a lot of utility out of treating it also as random. Okay, so that's the plan. Let's think about a very simple model on a contact network of who comes into contact with whom, and then think about a biological contagion that's spreading via these random processes, these coin flips. And so the simplest model that people consider is sometimes called the branching process model. And the thing to picture is, say we're in a crowded city, and this person arrives on an airplane or on a boat, and they have a disease that no one in the city has ever encountered before, right? And they're sick with it, and they're contagious. And they're going to go out into the city, and they're going to meet some number of people, okay? And so there's going to be a first parameter of the model, which is this number k, right? How many people each person meets when they're potentially infected with the disease. So patient 0 meets k other people, and that's the first wave of contacts, right? These people all came in direct contact with the affected person. Now, each of those people in the first wave goes out and meets k new people, and that's the second wave, right? K new people for each one of these people. And each person in the second wave meets k new people, that makes the third wave, and we're actually going to imagine this process going on forever, right? Now, clearly the city doesn't really have an infinite supply of people, but for the sake of creating the conceptually cleanest model that we can, we're going to have this infinite branching contact network. Everybody has k nodes below them in the next wave. Okay, that's the structure of the contacts. We haven't yet talked about how the disease spreads. The way the disease will spread is again by this coin flipping model. Patient 0 is sick, and with each of their k contacts, a coin is going to be flipped. The coin has a probability p of coming up heads, and if it comes up heads, the person they meet gets sick. Right, we're going to flip that coin independently for the k people that they meet. Right, so maybe, for example, patient 0 meets these 3 people, and the coin comes up heads on the first 2 and tails on the third one. Right, so the third one gets off scot-free. They came in contact with this sick person, but they didn't get sick. The first 2 now, however, are sick. They now are contagious. They go out and meet k new people each, and maybe the first one infects 1 new person, the second one infects 2 new people. So in the second wave, we now have 3 sick people. They each go out, and maybe some coins get flipped. The first one infects 2. The second one's actually a dead end for the epidemic, right? They actually infect nobody because 3 coins came up tails. And the third one actually infects all 3 people they meet. Now we've got 5 people. And if you think about it, actually, each of those 5 people is standing at the top of an infinite contact network that's continuing on down below them. It's like we've now got 5 copies of the epidemic running. And that, in a sense, is what's so frightening about epidemics once they get rolling, right? It's actually, when you're battling an epidemic, it's almost, in this picture sort of reinforces that. It's almost like battling a kind of, this multi-headed monster where, you try slicing off one head and more of them start growing, right? Where we once had 1 patient 0, it's like we now have 5 of these people, and they're all creating their own mini epidemic as it proceeds downward through the branching process. Right? And that's what's so dangerous about epidemics, and why people are so aggressive about trying to stop them early, because once they get rolling, you've just got a lot of people out there all passing the thing on. Okay, this one that we drew was quite an aggressive epidemic, right? So the probability P was fairly large. If P had been lower, it might have looked much more mild, right? So on the very same contact network, let's still take patient 0, and they go out and they meet K people, and coins get flipped. And maybe even though this is a milder epidemic, they still infect 2 people, maybe the second and the third one. But in the end, the odds are working in our favor because this has just a lower probability of infection. And so maybe of these 2 new sick people, the first one infects 1 new person in the second wave, and the next one infects 0. And so we get down to the second wave, there's only 1 sick person again. Right? The epidemic is really failing to expand, failing to replenish itself. And maybe, again, because it's a mild epidemic, we flip coins for this person in the second wave, right? They meet 3 new people, and they fail to infect any of them. And at this point, the epidemic is over. Everybody in the third wave is healthy, and from then on, no one's going to get sick. No one's going to continue the epidemic. And in that way, the epidemic has died out. So that's actually going to be the fundamental kind of question that we're going to be thinking about when we try to model this process, right? We've written down what's actually a fairly clean mathematical model, right? It only has 2 numbers in it. K, the number of people that you meet, and P, the probability of contagion. And the fundamental question we're going to ask in this model, and it's really a nice, well-defined mathematical question, is do we expect that the epidemic has a chance of running forever, right? Infecting people arbitrarily deeply into the contact network? Or do we believe that it is almost surely going to die out after a finite number of waves, right? It'll come to some wave, that will be the last case of this disease, the next wave will be completely healthy, and it's over. And what we're going to find is that this model is actually clean enough that we can analyze that trade-off, that distinction. Epidemic runs forever, rampaging through the population, or epidemic dies out. We're going to be able to analyze it in terms of these 2 properties of the model, right? K, the sort of branching of the contact network, and P, the aggressiveness of the disease itself. And that's the concrete question that we're going to take up next.